Should be working now. Is it? Where you usually save it? Down there?
Can you save it? That's my stuff. Can you save that?
Yeah.
Yeah, I was gonna say that at least it smells really good. It could be worse. How you guys doing? I'm so jealous.
Oh yeah.
Yeah. I'm gonna
Camera today also. Apparently they found it.
I asked Robert, and it seems that there's no one there right now. Chris is not there yet, so maybe.
Chris, oh, he just got in.
Maybe, yeah. Should I go?
Can you get another TA to go in?
Well, George is here.
Can you get someone else to go? Yeah, because you might have one. I need at least one more.
Anyway, so
That's fine. I'll take it.
Let's get started. Very quick announcements. There's nothing new right now, so that's a little weird, so we'll fix that. There should be a homework 4 that should be available maybe, hopefully, by the end of the day today or more likely early tomorrow morning. This will be all about learning theory. There will be no code, only math. And though I'm sure a lot of you complained that there was just too much programming and not enough proofs. So this one will make it happen. And some of you already got feedback about your projects. I'm hoping to get to the rest of it by soonish. Actually, most of you are doing the Kaggle thing, so I have to read the exploratory projects, only few of them carefully, only like about 30 or so. So you should be hearing back soon. Are there any other logistical things that you'd like to get out of the way? Oh, we are having some issues with the videos, so it seems like the video quality would be somewhat less than optimal. Let's put that, let's keep it at that. I'll post annotated slides on the class website as well, so that you have some recollection of that. And I'll also add pointers to the previous year's video of the same lecture. Boosting and ensembles that we'll cover today has not changed much in the last 1 year, so the content is still the same. So, any other questions? Yeah?
So for the final project, we have to implement 5 or 6 algorithms.
6. You're doing the Kaggle thing?
Yeah.
Yeah, so you need to do 6 algorithms, you need to compare 6 algorithms. Essentially, you need to submit at least 6 runs.
Are we actually going to get that as assignments where we learn?
So, I expect that in your assignments you'll implement at least 4. You've already done 2. In your assignment you'll implement at least 4. A 5th one could be a minor tweak. For example, let's say you've already got perceptron and decision trees, you'll implement support vector machines and maybe some version of ensembles. And logistic regression is going to be a really tiny tweak to support vector machines and perceptron. So you get 5. And the 6th one, I expect, the 6th one could be a variant of one of these things. Say for example, if you do boosted decision trees, the 6th one could be some other ensemble. Or the 6th one could be something that uses machine learning library. If you feel like you want to use TensorFlow or scikit-learn or something, we'll have hopefully somewhere down the line we'll have a lecture where we just talk about tools. You can use one of those tools or just pick one up. Or the 6th one could be just a variant of any of these things. Yes?
So variant meaning like aggressive perceptron versus market perceptron?
Sure. Yeah. Or it could be additional features that you invent, something that you try, or something that is different. So what I expect is any of the algorithms that we cover, which basically would be the first 5 runs, The first 5 submissions, any algorithms that we cover in class, I expect you to do implement them on your own, same rules as the homework. And for the 6th one, you are welcome to use a library. Any questions? Yes.
I feel like it was either last week or the week before, there was an announcement about making like at least 2 non-dummy submissions.
Yes. So I was going to announce that in the next on the next lecture. But there will be an intermediate status report. That is, I think, November 15th or 16th or something like mid-November. It's called intermediate, but it's so close to the end of the semester, it's kind of awkward. But the idea is by then you'd have had to submit at least 2 runs, non-dummy runs. And the good news is you already have 2 algorithms implemented, so you could do it. But I was talking to somebody in office hours, I think recently. If you just take your decision tree from the homework and you run it, it's not going to work. For the simple reason that there are how many features? Like I can't remember. 73,000 features. So it's going to be problematic. So the thing to do is you need to think about your implementation a bit. The best thing you can do to make your code fast in this case is to use the observation that in your project data, the features are extremely sparse. There is no example. So the examples are 73,000 dimensional vectors, but almost every element of that is 0. So there are maybe 20 or say 100 non-zero entries. So what you need to do really is to store the non-zero entries in a key value kind of a pair. So the feature number 17 has a value 1, feature number 23 has a value 1. You don't store the zeros and make the default 0. So the advantage of that is every example becomes extremely tiny. So this basically gets over the memory overhead. One of the problems that you might run into is you don't have enough memory to actually run the whole thing with decision trees. So use a key value pair sort of stored to store feature vectors, store only non-zero entries. Depending on what language you're using, they could be called hash maps or hash tables, associative arrays or dictionaries. Most of you, I think, are using Python, so you do dictionaries. And this will really make your code more efficient. Just as an aside, on a very similar data set on a whim, I implemented a decision tree from scratch in Scala, and it basically finished running everything in like about a minute and a half. So you need to think a bit about your code, and it's totally doable. But if you want, we can kind of brainstorm ideas either in class or in office hours, or you could use Canvas to brainstorm ideas. Speaking of office hours, I forgot to put up an announcement, but I did send it out on Canvas. My office hours are no longer right after class on Tuesdays. They are at 4 p.m. on Tuesdays because apparently one big group of you are in the algorithms class, another big group of you are in the models of computation class, so nobody can make it to office hours apparently. So I figured rather than me sitting by myself at 11, you guys can show up at 4 o'clock and we can talk about stuff. Alright, any other questions? Yes?
If we want to pick up the exam, do we have to come to office hours or we can just stop by your office and
If my door is open, you can stop by. Or come to office. Alright, so we're going to continue with lectures. Today we're going to look at boosting and ensembles, a really big topic which is probably worth many lectures of its own, but given the constraints of the class, we're going to try to squeeze everything into one lecture. But before getting into that, I just want to step back up and take stock of where we are, what we've seen so far. And I like coming back to this because I want to point out that everything that we are doing in the semester is kind of feeding into essentially this slide. So we are doing supervised learning. This entire class is almost, all of it is about supervised learning. And the setting is that we have instances that are going to get assigned labels. One of the important things that you need to think about anytime you want to frame any problem you have as a machine learning problem is what are the instances that are getting, say, featurized, that are getting labeled. So if you are building an image classifier, your instances are images. If you are building a classifier that classifies, say, spans of text into some categories, your instances are not the entire documents, but just the spans. Those are the things that go into the classifier. Now, though your instances are whatever gets classified, typically you get features. Your data is featureized. Did you get a camera? No? Okay, we'll figure something out. So your instances are typically featureized because you need to map your the instances, which are objects in the real world, into a vector space, into some sort of attribute space, so that your learning algorithms can actually reason about it. Keep in mind, your learning algorithms can only handle things that show up in features. You want to classify cats as being tabby or not. Your code does not know how to talk to your cat. Sad as it may be. So we're talking about supervised learning, where the idea is that you're given some labeled example. There is someone or something that has labeled your data, and all of this gets thrown at a learning algorithm, and the learning algorithm is an algorithm that takes labeled data and produces a model, or a hypothesis, or a classifier. All of these things are really the name of a function that can take example and assign labels to them. So once this learning is done, the classifier can go around labeling new things. Under this umbrella, we've looked at least two different learning algorithms, decision trees and perceptrons, and many variants of these things. But we've also encountered general machine learning ideas that are applicable not just to these algorithms, but more broadly. I mentioned the idea of instances as features, and features being high-dimensional vectors. The crucial thing that you have to permanently keep in mind is the risk of overfitting. Your learning algorithm, if you don't actually take care, might end up remembering the training data. And remembering the training data is not necessarily as great a thing as it sounds, because the goal is not to remember, but to generalize. So the underlying objective here is to label new things, is to generalize to unseen situations, which, speaking of underlying goals, we can ask what does learning mean? And we looked at least two different answers to that question. One of them is in this mistake bound sort of model, where we said learning is is said to be done when the classifier stops making mistakes after seeing a stream of examples. This style of reasoning gives us online learning. Another way of thinking about the same question, what does learning mean, led us along the path of pack learning. Pack learning is where we talk about how can we find, with high probability, can we find a classifier that is really good, that's close to perfect. So this style of reasoning, this is what we were doing for the last couple of weeks, gives us, it's generally, when people say learning theory, they usually mean either pack learning or online learning. But the pack learning gives us generalization bounds. It gives us, it includes the ideas of sample complexity. We looked at agnostic learning, where you believe that your classifier, your model may be somewhere here, but you really can't search the space, so you go somewhere else and search this other space because it's easier to search. And then you can ask, how good can your best classifier be? And then in the last lecture, last week, we looked at DC dimension, where we extended these ideas to infinite hypothesis classes. And we said, how do you measure complexity of these kinds of functions? They're infinite when there are infinite of them. So under pack learning, and actually even in the mistake bound, both of these things really give us the same underlying message, which is if you can avoid it, avoid complexity. Don't make your hypothesis space too big unless you need to. Your hypothesis space should be as big as it needs to be. Now, of course, that's a vacuous statement. How big should it be? I don't know. Depends on your problem. But in general, it gives you this inductive bias for learning, namely preferring simplicity. Any questions? This is roughly where, this is like a maybe 5-minute overview of everything that we saw. Any questions? If there's nothing else that you learned from this class, I strongly want you to take back this message, which is prefer simplicity. Occam's razor is a good life philosophy. So today what we're going to do is look at this idea of ensembles or ensemble learning, but I want to introduce it through the specific question or algorithm called boosting. So we'll first look at what is boosting, and then look at a really cool algorithm called add a boost, which is a meta learner. It takes a learning algorithm and in some sense boosts it into being better. The same philosophy can be expanded into other kinds of algorithms which are actually rather simple to describe but tend to be rather robust. So first let's start off with what's boosting. It turns out the question that motivated boosting was it came from a question that was a theoretical question from this paper called The Strength of Weak Learnability. So just to set the historical stage, the theory of pack learning was introduced, the definition of pack learning was introduced in 1984, and in 1988 or something, the whole it was expanded to this sort of agnostic and the whole idea of using VC dimensions and all of that. So whatever we call pack learning, let's call that strong learning, strong guarantees. So boosting was this question that talked about is a general learning approach that can construct a classifier that has strong pack guarantees using a collection, maybe an infinite number of them, but a collection of weak classifiers, or think of them as rules of thumb. So you have a whole bunch of rules of thumb that you can invent really quickly. You want to somehow combine all these rules of thumb to get a single classifier that has strong pack guarantees. It turns out it's a very useful idea because we can invent rules of thumb very quickly. More broadly, it's an instance of this class of methods called ensemble methods, where an ensemble is really like a committee. You have a collection of classifiers. Instead of believing any one classifier to be right or wrong, what you do is you group them all and ask them to vote on the answer. And you take the most, the average vote or the most common vote or something like that. This idea of getting, decisions from multiple experts or multiple even weak experts, and kind of making the consensus being more robust shows up historically. It has shown up in many, many places. Have you all heard of the story of Francis Galton and the cow? Okay, I'll tell you the story. It's a bit of a digression, but it's fun. So, Sir Francis Galton, he's I'm not sure what he was. He was like a geneticist, biologist. If anyone knows better, correct me. The story goes, who knows how true this is, he goes to some fair in England. He lived in England in the early 20th, late 19th century. And he wanted people to guess the weight of a cow. He invited a whole bunch of villagers, and his idea was, these are ignorant villagers, they know nothing. How could they possibly be right? So he wanted them to guess the weight of a cow, and it turns out they were all really bad. Because they were all off. I mean, they were farmers, they worked with cows, but they didn't know what the weight was. I mean, understandably, it's a fair point. So he went home feeling all happy that he was proven right, that these people are ignorant farmers, they know nothing. But being the honest scientist that he was, he decided to analyze the data. And he actually took the average of all the predictions and he found that the consensus was almost perfect, just looking at the curve. This is a famous paper called The Wisdom of Crowds. And in some sense, you can think of ensembles as being this similar philosophy. You have a collection of decisions that are being pulled together, and this collection tends to be more robust in terms of error, provided some conditions are satisfied. Of course, if the entire collection is poisoned, the consensus is also bad. Let me give you an example. This is a bit of a dated example that comes from your friend, or maybe Bob Shapiro, one of the people who invented the AdaBoost algorithm. And it's from the 90s, which is why you have these things like calling cards in the example. So let's say you operate this service that routes telephone calls to different other services. So if the customer picks up the phone and says, I'd like to make a collect call, please, it has to go to this thing called a collect call. I have to confess, I'm not entirely sure what a collect call is, but we do that. If let's say you want to make a call and you want someone else to pay for it, it goes to another service called third number. If you want to make a call but you want to bill a specific credit card for it, it has to go to this thing called MasterCard. Sorry, calling card. So you can think of this as a classification problem. The classification problem is you're given some utterance and the goal is to find one of maybe 3 services that best satisfies this request. And the important observation here is that rules of thumb tend to be really good. So if the word card shows up in the utterance, it's probably a calling card. You can invent these rules of thumb really, really quickly. You can invent lots of them and they would be reasonably good. But unfortunately, it would be hard to humanly write down a single prediction rule that covers all cases. So far, so good? So the question is, can we somehow pull together all these rules of thumb and boost them into a single prediction rule that will be good? And by good, really, what in the original definition, in the original paper, by good, what Rob Shapiro meant was, will you get a prediction rule that has packed guarantees? And there were many. So this was a challenge that was laid down to the machine learning community in that late 80s paper. Very early on, I think it was Shapiro himself who came up with a single an algorithm for boosting. The idea was you select a small subset of examples and you invent a rough rule of thumb. You select another subset of examples, you invent another rule of thumb, you invent another one, and you keep doing this many, many times, 3 times, and you combine them into a prediction rule. This is like a very loose thing, but this is not an algorithm. What does combine mean? What does invent mean? We still need to specify how to select a subset, we need to specify how to combine the rules of thumb and all these things. And boosting is a general method for converting these rules of thumb into a single classifier. So before formalizing this, are there any questions about the setup? Yes?
Can a second rule of thumb make knowingly contradict your first subset of examples?
Nothing in the algorithm we'll see prevents that. It could. And we have to somehow reconcile these things. That's what this combined thing has to somehow do. So let's formalize this. Whatever we called pack before, I'm going to call that a strong pack algorithm. So a strong pack algorithm for a quantum class is an algorithm which, for any distribution of examples, for any epsilon and delta, given a polynomial number of examples, will find a classifier whose error is less than epsilon. But it may not always find such a classifier. It finds such a classifier with high probability, with probability at least 1 minus delta. So with high probability, this algorithm will give you a good classifier. This is basically the pack thing. And an algorithm that does that, let's call that a strong pack algorithm. Now, in order to formalize this idea of a rule of thumb, let's define something called a weak pack algorithm. A weak pack algorithm has the same guarantees, but the error is really bad, meaning it's just slightly better than chance. It is just half minus gamma. Half minus gamma is, gamma is positive, is a positive number, so half minus gamma would be maybe like the error is 49% error. Same guarantee. So notice that this is for any epsilon greater than 0. A weak pack algorithm has an additional guarantee, additional requirement that the epsilon is close to half, but less. Okay? So weak pack algorithm is an algorithm that with high probability will get you a classifier that is just slightly better than chance. Let's call that a rule of thumb. So a weak pack algorithm is an algorithm that produces rules of thumb. Now the question, and this was a question that came up, this was a challenge that came up in this paper by Kearns and Valiant. If I give you a concept class and I tell you that I have a weak pack algorithm, does this guarantee or does this mean that the concept class is learnable in the strong sense? Does there exist a strong pack algorithm? So, and this is a pretty natural question because most of us find it very easy to invent rules all the time. But we also know very well that these rules are going to break very quickly, and that's why we need machine learning. Now, essentially this question was asking, if I give you some sort of a concept that for which the rules of thumb are easy to invent and the rules of thumb are reasonably good, does this mean that the concept class itself is learnable in the strong sense? Before we move on, are there questions about this problem, that statement? Yeah.
So you're trying to say that if you can't come up with these rules of thumb, then you should be able to also create a strong way.
Let me almost. What I'm saying is, really, there's a question. I want you to kind of digest the fact that if I'm able to come up with rules of thumb, it does not necessarily mean that the thing is learnable in the strong sense. It requires a theorem. It requires a proof. We haven't looked at a proof yet. I've kind of given away the answer already because we have this chapter called boosting. But at that time, this was an open question. We did not know at that time whether a weak guarantee implies a strong guarantee. Maybe it does, maybe it does not. Maybe this concept class is learnable in the weak sense, but that's pretty much the best we can do. Because maybe the weak pack algorithm is the best that can exist and there is no strong guarantee.
Would it have to do with the number of samplings that we did?
Or essentially, basically it means, so just to unroll this word same, what I mean is a weak pack algorithm is one which for any distribution over examples, for any epsilon slightly less than half, for any delta greater than 0, given only a polynomial number of examples in epsilon and delta, the weak pack algorithm will find with high probability a weak classifier. Yes?
So just to think about this conceptually, if you can find a rule of thumb that's better than chance,
Yes.
that means that that rule of thumb is, the mere existence of that rule of thumb means that there's something predictable about the data, even
That's
if
the
it's
hope.
only slightly predictable.
That's the hope.
So if you have a lot of those that are all unique, they aren't the same, then added together, they kind of mean there's a better chance that this data is predictable.
That's roughly the intuition, yes.
Okay.
I think you said it well enough that I'm not going to repeat it.
Okay.
Yes. So, this was the challenge, yes.
Suppose we have a reclassifier, and a reclassifier is something we have right now.
you're talking about the existence of the strong classifier. Yes. So we have a weak classifier. We have a weak learning algorithm. I want to separate out a classifier and a learning algorithm. We have a weak algorithm which produces weak classifiers. Now, the question that Kearns and Valiant asked was, does this mean that there exists another learning algorithm which is a strong learning algorithm? And just to give away the punchline, the answer is yes. There is a strong learning algorithm that can compose all these weak classifiers that the weak learner produces to produce a consensus classifier.
How much is it?
How much is enough? That's a different question. We'll get to that in a theorem. So this was a question in 1988, and very quickly, people got interested and started working on this and produced early positive theoretical results. The first one was that earlier paper that I mentioned from 1989. Rob Shapiro essentially answered the question in a year. He said, yes, it is doable, and it was a rather kind of nuanced algorithm, which what you do is you call the weak learner 3 times, you get the fundamental idea that he introduced in this was, you're given a collection of examples. At the beginning, you assume that all examples are equally important. But maybe, once you get a rule of thumb, the examples where that rule of thumb is successfully predicting are going to be less important, so you downweight their importance, you upweight the importance of the ones where there were mistakes, and you modify the distribution over the examples, the importance. I say distribution, but essentially think of it as modify the importance of the examples. You do this 3 times, and then you kind of do, he showed on paper that you can get a slight boost in accuracy, and you keep doing this again and again. Now you apply this recursively, and it was a tricky argument, but essentially he showed that yes, weak learnability implies strong learnability. And then Freund joined the game, and he showed a theoretically optimal version of this thing. And then there were a few, very soon after, they tried some real experiments and found that this really doesn't work. It didn't work not because it's incorrect, but there were practical limitations. The algorithm that Shapiro proposed was not really friendly to implementation, let's say. Freund and Shapiro joined forces, and in '95 they introduced this algorithm called AdaBoost, which not only had strong theoretical guarantees, but also was practical. And once again, I like to use my measure of practicality as can I fit it in one slide? And yes, we will see the whole algorithm in one slide. So this is actually considered to be a really big step, at least for Freund and Shapiro. A whole bunch of papers followed that showed how you can use it and what it really does, what it means, theoretical analyses and all these things. And along the way, it also got a Godel Prize for the authors. So this shows, Shapiro started working on this in 1988. The prize showed up in 2003. So some lesson there about, persistency and how to do PhDs and all that. All right. So let's now look at AdaBoost itself, because all these other things are subsumed by AdaBoost. So let's look at AdaBoost. AdaBoost is not the only boosting algorithm that exists. There are other boosting algorithms, there are gradient boosts and all these things. But we're going to look at AdaBoost because it captures the idea, and hopefully if you're interested, you can find other resources that you can read on your own. I'm going to introduce AdaBoost using this example that, again, is from, I think, one Shapiro's talk. Imagine that you're given a collection of points, pluses and minuses like this, and our weak rules of thumb are either horizontal lines or vertical lines. We are only allowed to use these classifiers, which means this is a classifier that says everything here is positive. This is another classifier, and maybe this is a classifier, or maybe this is a classifier. Our only classifiers are either horizontal lines or vertical lines. And like I kind of hinted at, the entire trick or the entire the clever bit here is the idea that you assign weights to examples. And initially, you start off by assuming that all examples are equally important. And you try to find a rule of thumb. In order to find the rule of thumb, you call whatever learning algorithm you want to find a weak classifier. Let's say we find this one that assigns this function h1 is, let's say, the best classifier on this data, and it says everything on this side is positive and everything on the other side is negative. So it doesn't matter how you found the rule of thumb, let's say you found it. Now you have one classifier. Of course, this is not perfect. It makes 3 errors. Let's now keep track of the errors also. This is the classifier h1. It has an error epsilon 1, which is 0.3. So far, hopefully there is nothing shocking. Hopefully there is nothing shocking even after this. But so what you do now is now you increase the importance of all the examples that where your original classifier made a mistake. So I hope you see that the 3 pluses are bigger, and you decrease the importance of all the examples where the original classifier was right. So you upweight the importance of all the examples where your current rule of thumb is bad. You downweight the importance of all the examples where your current rule of thumb is good. And now you find a new classifier. So, but before that, you just remember the classifier that we just had. We're going to use this later, so just put that somewhere. And now we have a new data set. Now we are back to the beginning. We have a new data set, except unlike the beginning, where all examples were equally important, here, those 3 pluses at the top are more important. What that means is you need your weak learner now has to discover a rule of thumb, and it has to try hard to make correct predictions on the 3 pluses. So, in some sense, the cost of a mistake on these 3 examples for the weak learner is going to be higher. This kind of learning is called cost-sensitive learning, and most algorithms can be modified with slight modifications, can actually be made to be cost-sensitive learners. As an example, if you're doing perceptron, the cost could factor into the learning rate. If the cost is high, the learning rate becomes large. If the cost is low, so you basically multiply the learning rate by the cost. So more important examples are, force the perceptron to make bigger changes. As an exercise, I want you to think about how to do this for decision trees. It's slightly more complicated, but I'll leave that to you for now. You can come back and ask later. Let's assume that we have that, and now we want to use the weak learner again to find a classifier that classifies these things correctly, and maybe this time it finds a different rule of thumb. It finds a different rule of thumb, and notice that because we assigned the weights, because these 3 examples were had higher weights, they are now correctly classified. There's no requirement that should happen. This is a toy example, so we can make whatever we want happen. So now we have this. So now we have another weak classifier. How many mistakes is this rule of thumb making? 3, right? So let's help you. Oh, it's these 3. Right. Now it's these 3, but notice that these 3 examples are not as important as the big pluses. So what we need to do is we need to redefine our notion of error of this hypothesis. The error of this hypothesis is not 3 out of 10, I think there are 10 examples, but really it is the sum of the weights of those examples. If this particular example had a weight of 0.1, and let's say this one had a weight of 0.0001, and this one had a weight of say, I don't know, I'm just making up numbers here, so let's say 0.1. Let's say that it's not all 1, so let's put a 7. The error of the classifier is the sum of these three numbers. I'm not going to bother to add them up. On the other hand, in the earlier case, all examples were equally important, so the error of the classifier was the sum of their weights. So it's the same thing. So the error on this classifier is not 3 out of 10, not 0.3, but just to invent a number, 0.21. It's less than 0.3 because those three examples are less important. Does it make sense? And this there tend to be 2 points of pain with this algorithm. One of them is this question of how do you find a rule of thumb that respects this sort of importance of examples? And the answer is basically you mess around with the step size. Essentially, that's what it comes down to. For these perceptron-like things, for decision trees, it's something else. The other sort of somewhat different point here is the error is not just decided by counting the number of mistakes, but by aggregating the importance of the mistakes. Questions before we keep going? Yeah.
Does this algorithm depend on the order of like guesses that you choose? Because what if I chose a horizontal line?
Oh, it totally does. It actually does depend on the order. And the algorithm does, but oddly enough, the theorem does not. Which is kind of cool. Yes.
I don't have a real question.
Okay.
If
So
we have a series of deep learning, is there a way we can compress deep learning?
you could, but the theorem does not need you. So you could do the extra work if you want to, but you're not going to get too much more. Okay, so you're all kind of stepping ahead, at least the two of you, so am I. So what we're going to do is we're going to weight each example by this dt. So dt of I is the importance of example I in round B. So really, currently we are in round 2. So this would be D2 of whatever that example is, and then we just add up the D2 of those examples. It turns out that if you read the original work, the error is defined to be something like this. It is half minus half times sum over all the examples dt times yi h of x. And it turns out this is a perfectly reasonable definition. And I will kind of give you a hint as to why this is correct, or why it captures the intuition that I just described. Let's consider two cases. By the way, we are assuming that we have binary classification here, so the prediction, the label space is -1 or 1. So what happens when y, the prediction for an example, is not equal to the true label? Sorry, the y is the true label. If the true label is not equal to the prediction, what is y times h of x? It's -1 really, because we have -1 and 1. And here, y times h of x is +1. So really, these things are either -1 or +1, depending on whether there was a mistake or not for that example. Right? Now, so, okay, I just wanted to write that again. It turns out that you can use exactly that idea, and with very, very minimal sort of algebra, prove that the definition of error, epsilon d, is really asking, enumerate all examples where there is a mistake, where yi is not equal to h of xi, and add up the weights, dt of I. So that's what I just said earlier. So these two things are actually equal. It's not, the thing above is somewhat unpleasant to look at, but really that's what it is. So really, the error at any time, at any round, after any round, is the sum of the the sum of all the weights of the examples where the current weak classifier, current rule of thumb, made a mistake. So we add up the weights of those three circled examples there. So what we have, but stepping up a bit, what we have at the end of this round 2, is we have a weak classifier and we have an error. You do the same thing again. You upweight all the examples where the current weak classifier made a mistake. The ones where the current weak classifier made a mistake, and you downweight everything where the current weak classifier was right. Just as a point of observation, the three examples that were upweighted earlier are going to get downweighted now. So you increase the importance of all the examples where the current rule of thumb got the right label, so that the next time you'll be able to find something that classifies that fine. And you decrease the importance of all the examples where the current rule of thumb was right. Now, what happens as a result is if a certain example is consistently correctly classified, its weight keeps going down. So it doesn't matter. So later rules of thumb are not going to bother about those examples that have been correctly classified so far. And we repeat. Yes?
So do you just downweight the currently classified examples, or you downweight all the currently classified examples?
You downweight all examples that are correctly classified by the current rule. So at any point you have a data set and a rule, right? So you, just as an thing here, you downweight this one, you downweight this one, you upweight this one, up, down, and down. Because this rule of thumb made these mistakes.
And all by the same.
We'll get to the actual upweighting and downweighting factor later on. It turns out it's going to be the same thing. But yeah. So now we have two rules of thumb. It turns out we also came up with their errors, epsilon 1 and epsilon 2. We had those also. And we have a new data set where every example has weights. You know what to do. Call the weak learner again and ask for a new classifier that cares more about an example if that has a high weight. Let's say we get this horizontal line this time because we have that. And once again, this horizontal line also it's not perfect. So it makes 3 mistakes. It's just an accident that they always seem to make 3 mistakes. It makes 3 mistakes, but the error is not 0.3. The error, again, is the sum of the weights of those 3 examples, and it just so happens that those 3 examples had really low weights anyway, so the error is not 0.3 but 0.14. Any questions? Yes?
So when do we stop?
When do we stop? That's a very good question. The simple answer is you stop when you run out of time. It's a hyperparameter. In this case, I stop when I run out of time because 3 is too much. So what you have now is at some point after enough number of rounds, you decide that you've had enough rules of thumb, and now the goal is to combine all of them. What AdaBoost wants is every rule of thumb is going to be combined in a linear way. The final classifier that the AdaBoost algorithm returns is essentially a linear combination of all the classifiers that we've seen so far. I've not told you what the alphas are, we'll get to that later, but in some sense what's going on is, really it's the sign of this thing. What's going on is each rule of thumb is a function that produces a minus or a plus. For each of those things you assign a weight, an alpha, and you combine all of that, and you get a number for an example, and you see if that whole thing is positive or negative, and that's the classification that the final consensus classifier is going to produce. So really what's happening here is classifier H1 makes a prediction, and it gets a vote of alpha 1. Classifier H2 makes a prediction, and its prediction gets a vote of alpha 2. H3 makes a prediction, that prediction gets a vote of alpha 3. All the votes are aggregated, and the final prediction is consensus defined this way. So think of these alphas as votes for each weak classifier, and of course, the boosting algorithm is not complete if you don't say how to produce these alphas. So let me just quickly summarize everything that we saw before. We are given a training set, M examples, x1, y1, x2, y2, and so on, where each xi is in some instance space. I don't care how you featureize these things here. We don't. Those are problems for the weak learner to deal with. The labels are -1 and 1, and now you start generating weak classifiers in sequence. What you do is at every step, every round, you first construct a distribution over the examples. This is just the importance of each example. You somehow need to specify what's the importance of each example, and then the weak learner comes into play. You find a weak classifier that has small weighted error somehow. Let's call that the weak rule of thumb. Let's call that HT in the Tth round. You do this enough number of times, capital T number of times, and you have T weak classifiers or T rules of thumb, and you construct the final output, and you're done. This is not really an algorithm, because there are two important steps that are missing. One of them is how do you construct these distributions, and the other one is how do you construct the final output. I am skipping another important step, which is this one, because that's any learning algorithm. Nothing here requires you to use a particular learning algorithm or another. All you need to do is augment the learning algorithm to produce a classifier with small weighted error. Of course, there's another step which is the for, but I'm assuming all of you know what that is. So really the two important things are how do you construct a distribution over the examples, and how do you construct the final classifier by combining the rules of thumb. And that's what we're going to look at next, unless there are questions. Yes?
So the final hypothesis is no longer a linear classifier, and because of that, the BC dimension would be like a lot higher.
Oh, that is so right. Yes.
So how does that impact like how many examples we need, or does this actually just be better in general?
That is the uncomfortable question about boosting. It turns out that the final hypothesis, capital H final here, is not in the same space as the rules of thumb. It comes from a family of classifiers that has a different VC dimension, a higher VC dimension, and somehow it seems to work, and there are conjectures or explanations for why this happens. We'll come to that once we see the outcome. But yes, that's a very insightful observation. It is true that the final classifier that we here, for example, by adding up these three things, we'll get a classifier that is neither a horizontal line nor a vertical line. So we are getting a classifier from a larger family of functions, which means we have increased the complexity, and this seems to go against Occam's razor. Because it seems like, this is weird. This is not, we have somehow made the problem harder because we demand more examples, and yet some good things seem to happen. So we'll get to that when after we see the algorithm. Okay, so two things left to do. One is how to construct the distribution, and two, how to construct the final output. So let's look at them in order. Constructing the distribution. What I mean by distribution is at every round you have a set of weights over the examples, and sadly we use the word weights all over the place in machine learning. We use weights to weight features, we use weights to weight examples, and this can get slightly tedious. So sometimes I might call this costs for each example, but the slides are going to say weights. So at every round, we need to construct this distribution. I call it a distribution because we will see later on that our choice of this actually is such that these things add up to 1. And at every round, the weak learner has to find a hypothesis that that gives more importance to examples which have a higher DET. So if an example x, y, xi, yi has a very high weight, the learner has to try really hard to find a classifier that classifies that example correctly. That's the role of these costs. At the beginning, what you do, as we saw in the toy example, all examples are equally important. If you have m examples, you initialize the weights to be all 1 over m, so the uniform distribution. This is not there's nothing exciting here, so let's move on. Let's now assume that we've been running this thing for t rounds. After t rounds, what we have is we have the tth distribution, that is dt. Using dt, a hypothesis ht was produced, and that ht had an error of epsilon t. Right? So you have a data set with distribution dt that produced a hypothesis ht which had an error epsilon t. So these are the 3 things that we have. Now the goal is to now say how to construct dt plus 1 using these 3 things somehow. We're going to define a way to construct dt plus 1 using these 3 things, and at that point we will have all the information we need because we know how to produce d1 and we know how to produce d2 because we have d1, we have and so on. So we can keep constructing dt all the time. So we want to the intuition is we want to find from the t plus 1th round, we want to somehow emphasize examples that this particular hypothesis was bad on, and we want to de-emphasize examples where the HT got the right hit. So we want to increase the importance of misclassified examples and decrease the importance of correctly classified examples. So that should be the shape of any update to this D. Any update to D should upweight or promote examples that were incorrect. What AdaBoost requires is, it says, construct dt plus 1 as follows. For every example, for the ith example, what you do is you take the previous dt, and if the prediction was correct, you multiply it with e power negative alpha t. If the prediction was incorrect, you multiply it with e power positive alpha t. When will this, and this is z, which is just a normalization term. Zt is just you add up all these things and divide, and z is just a sum of all these things, so that you get a probability distribution at the end. So if you had something like, we'll get to the z's later, but I can simplify both of these things. Whenever this quantity is true, the yi times h of xi is what? It's positive 1. Here, the same quantity is negative 1, which means I can, whenever this is positive, you have a negative here, whenever you have a negative here, you have a positive here, so I can put minus alpha t. Right? So, what we have here is just a way of constructing. Keep in mind, you could come up with a different way of constructing the dt plus 1. But the more important thing is it needs to satisfy the property that we require. It should promote correctly predicted examples and demote incorrectly predicted examples. Yes?
What if you took the approach of just every example that was incorrectly classified, add an additional occurrence of that example to the data set.
This is in some sense simulating that, but I think this is interestingly, when I first learned about boosting, that's literally how I implemented it. And it turns out this is a more robust version of that.
Okay.
Yeah. So when you promote, but also if you want to do that, see, you can do what you want. You need to prove that it's good. Anything, an algorithm is not an algorithm until it comes with a theorem. Otherwise, it's just a heuristic. So you need to have a theorem that says what you do is good. In this case, Freund and Sheffield gave the theorem. Yeah.
So, yi times HR, right, is a binary value. So,
Yes.
how complicate things by adding an exponential factor? You just
Oh, so that the theorem actually works.
so instead of multiplying the exponential adding by 3 or 4 or something.
You could do that. Then prove the theorem. Here. I'm not saying they're not viable alternatives. It's entirely possible they could be. It's entirely possible that particular alternative that you just suggested could show up in a homework. But then you'll have to prove that it's correct. You see my point, right? I mean, it's not enough. There are multiple ways of promoting and demoting the examples, but we need the one where we can actually show that it gives us some sort of guarantee on the error eventually. So, just to kind of point out that this is correct, this does actually promote or increase the importance of incorrectly predicted examples, because if alpha t is positive, and we will see a way of constructing the alphas that guarantees that alpha is positive. If alpha t is positive, e power alpha t is always positive, so you multiply this with this quantity, you increase the dt. If alpha t is positive, e power is always positive, but what I should have said, let me repeat this. If alpha t is positive, e power alpha t is greater than 1, which means multiplying this thing by a number greater than 1 is going to increase it. If alpha t is positive, this quantity is going to be between 0 and 1. Multiplying dt with a number between 0 and 1 will decrease it, so this at least meets the goal that we had. There is this z that we need to worry about. Not going to worry much about z really. Z t is the sum of, or I equals 1 to m, t of I times e power so really it's the sum of this numerator over all the examples. So what that will give you is it guarantees that dt plus 1 is going to add up to 1. So it gives you a distribution. That's why it's called a distribution. So we're not going to worry too much about the z's. It's just a normalization constant. It does matter later in the proof, but we don't need to worry about it now. The other thing that we need to show is how to construct the alphas. Remember we had these errors, right? We had when we had at the beginning, when we wanted to construct this thing, we had dt, we had ht, and we had the error. Alpha is defined in terms of this error. It's defined to be the half log of 1 minus epsilon divided by epsilon. And this may seem like a strange choice, but it kind of meets the requirement that we had. Remember, all of these things are happening only when alpha is positive. So let's examine what happens when we have this. If you have a weak classifier, you know that the error is going to be less than a half. It's close to half, but less than a half. If error is less than half, this numerator is more than half, and this is less than half. So you get a number that's more than 1, so this quantity is always positive. So alpha is always going to be positive, so AdaBoost requires that you use this definition of alpha. Eventually, it's the same. These are the same alphas that serves as the votes for the weak classifier. So the hypothesis ht that we had gets a vote of alpha t, which is this quantity. Every classifier gets a positive vote. Yeah.
When So when the error is greater than a half,
This whole thing breaks down.
but it would be alpha would be negative. So would it contribute like a negative vote? Like
In some sense, if the error is more than a half, alpha is negative, so it contributes a negative vote. What that means is that this weak classifier is so bad, if it says positive, you take negative, if it says negative, you take positive. So it still kind of serves the purpose. You always, the weak classifier is a liar, is what it is. So what we have done now is just to kind of go up the stack, we have a way of constructing dt or dt plus 1. Given dt, you can now construct dt plus 1. dt plus 1 is defined to be this quantity here, where that uses the alpha that's defined here. So that takes care of the first of these two things that were required. The only thing left is to specify how to construct the final output. And I've already given you a hint. When you have the final output, when you are at the point where you need to construct the final output, you have run this process t steps. So you have t weak classifiers, h1 to ht, and you have all these t alphas. You computed them, why throw them away? Now the alphas are the ones that are going to be the votes for each classifier. Now the weak classifier itself is a classifier. It takes an example and produces a label. The label is -1 or 1. What Adamos defines the final classifier to be is this thing here. You add up all the predictions of the weak classifier, but weight each of these by alpha t. So if the higher the value of alpha, the more you believe that particular rule of thumb. The lower the value of alpha, the less you believe it. You add all those things up, and you take the sign of it, the consensus. Because keep in mind the alphas are always positive here. So in some sense, it turns out the final hypothesis for AdaBoost is a linear classifier, but not a linear classifier in the original instance space, but it's a linear classifier in the space that essentially these rules of thumb can be seen as feature transformations. Right? So you're taking the x's, converting these new feature spaces that only consist of -1s or 1s, and the alphas are the weights that are learned for that transformed feature space. Questions? Let me, did you have a question? Right. So let me summarize the entire algorithm, and as I promised, I managed to squeeze everything into one slide. So you're given a training set, and examples are labeled as +1 or -1, and there is a hyperparameter, capital T. Capital T decides how many rounds this whole thing should run. First, you initialize all the distributions to be the uniform distribution. So for every examples, if you have m examples, you carry around m numbers, and every example gets a weight of 1 over n. And you start this, you start playing this game. At the tth round, you find a classifier, ht, that has low-weighted classification error. In fact, it doesn't have to have low-weighted classification error. All you need is that the epsilon should be less than half, right? So find a classifier that is better than chance, where the weighted error is better than chance, and you compute its vote. Alpha t is half log 1 minus the error divided by the error of that particular classifier. Now that you've computed the vote, you're ready to move on to the next round, but to prepare for that, you reweight the examples. You promote all examples where this particular ST made a mistake. You demote examples where ST did not make a mistake, and now you have dt plus 1. And you're ready to go back to the next round, the t plus 1 round. After running this thing for multiple rounds, you create the final hypothesis by just adding all these things up. And keep in mind, this is a function. The final hypothesis is still a function. It's a classifier that maps x to a label. In the toy example, the final classifier, just to remind you, would look something like this. And as Michael pointed out, the final classifier does not lie in the hypothesis space that we originally considered. It was neither a vertical line nor a horizontal line. It was some sort of a new hypothesis space that has been built up. So this final H final comes from a more expressive class of functions than what we originally started off with. Before I state the theorem, are there any questions? What I would like you to think about is how would you implement this? What would you need to implement these things? And you might, as you think about this, you might run into some sort of technical difficulties. Yes, there's a question.
Are there bounds on capital T to avoid overfitting?
There are no bounds on capital T to avoid overfitting. In fact, I know you're asking for the theorem, so let me just give you that. It looks like this. And I'm not going to prove this simply because I don't have time. I know. But the proof is on the class website. I know. It pains me. So what you do, the theorem assumes that let's say you have a data set and you run AdaBoost for T rounds. Define epsilon T to be the error of each of these weak classifiers, and suppose epsilon T is always is defined to be 1 minus gamma T, and if gamma T is always between 0, it's at least gamma, meaning you'll never get to half. Then the theorem says the training error for the final classifier will be less than e power 2 gamma square capital T, or e power negative 2 gamma square capital T. The definition of epsilon T that way basically says we have a weak learner, because epsilon T is, if you have, this is 0 and 1 and this is half, epsilon T lies in this region. Why can't I draw a curly bracket in this region? But it's actually closer to half, so this quantity here is gamma. And the smallest such quantity, the closest you get to half, is gamma, not gamma T, but gamma. So the smallest of all those things, the worst, gamma is defined by the worst weak classifier. What this says is, as the number of rounds increases, the training error drops exponentially. Keep in mind, it's a training error, not the generalization error. The training error drops exponentially. Now, why is training error a useful thing? Because remember from our agnostic learning lecture, the generalization error is bounded by the training error plus some ugly term that depends on the VC dimension. So if you have a low training error and you guarantee that the VC dimension is also low, generalization error is also bounded. The proof for this is actually extremely simple, and honestly, it's kind of fun. So there is a note on the class website which goes through the proof. I strongly encourage you to actually go through it and work it out yourself. And as you see the proof, you'll realize why these weird choices for alphas and the updates that you had asked about were made. It turns out all those choices perfectly are perfectly chosen to make the proof work. So, what we have is a bound on the training error. And I've already answered this question. It's not enough to bound the training error. You need to bound the generalization error, but let me give you some plots. The training error drops exponentially fast if your weak learners are better than chance. This is a plot of number of rounds versus the training error, and this is a very common plot. You basically find that you are in a situation where you have zero training error very, very quickly. What's the risk of getting zero training error? Overfitting. So you could be overfitting. As an aside, you'll also see that as the number of rounds increases, every individual classifier, the teeth weak rule, gets worse and worse. But this is not really overfitting. This is got nothing to do with it. What we start off with good rules of thumb, and as we go on, the rules of thumb get lousy. But that's just neither here nor there. What we care about really is the test error. What the theory tells us is the training error will keep decreasing, and it will go down to, very quickly go down to 0. But the test error we expect will kind of after a point go up. Why will it go up? Because, as I said, the consensus classifier, the H final, is a linear classifier in over all the rules of thumb. If you have t rules of thumb, the VC dimension is t plus 1. So as you keep increasing the rules of thumb, you're increasing the VC dimension, so we expect that the generalization error over time should keep going up because you will be overfitting. But in practice, something really strange happens. This is actually a real curve. In practice, the training error drops down to 0 and the test error does not go up. And when this was observed, of course, this is like, waiting for theory. So, of course, people got into action. And there are many, in fact, sometimes the training error decreases the test error decreases even after the training error hits 0, which is even more weird. So it turns out that there is actually an explanation for this. One possible explanation is in this paper by Shapir and Freud and Peter Bartlett and others, and Lee. There are, in fact, many explanations. Let me. One possible explanation is that as you keep increasing the rounds, you remember that linear classifier? Even though you're increasing the VC dimension, you're also kind of increasing the margin. And there's some theory that shows that increasing the number of rounds increases the margin, which is a good thing because more margin is better. But these are all kind of explanations that make awkward assumptions. Just to summarize what boosting is, first of all, what's good about it is it's a very simple method for kind of aggregating consensus of classifiers, and it requires only one more hyperparameter. Of course, there are other hyperparameters depending on what your weak learners are. For example, if your weak learner was perceptron, you had all the hyperparameters that perceptron gets. You can use this with any weak learning algorithm. And there are a few caveats. The performance depends on the data set you have, like any other learning problem. It's not magic, is what I'm getting at. And it also depends on how good your weak learners are. Once again, it's not magic. It can fail if your weak learners are really complex, because it might end up overfitting in crazy ways. It might fail if your weak learners are too weak, because it could underfit. There is some empirical evidence, and this will be the last thing I'll say today, from this paper that I really like from 2006 by Rich Kurwana, which shows that if you have a small number of features, let's say 300, then one of the best things you could do as a black box system, that let's say you want to throw a black box machine learning system at something, at data that you don't really want to think about, one of the best things you could do is to use boosted decision stubs. You know what decision stubs are. You know what boosting is. So now you can actually implement this sort of a really robust industrial strength learner. And it turns out to be surprisingly good for low dimensional problems. Maybe not so much for high dimensional problems, but definitely for low dimensional problems. And this should be like a tool that you should have in your toolkit. Parting words, a student that I was talking to a few years ago, just very recently, who was doing an internship, I think at Baidu or some search engine, maybe Google, was pointed out that, they advertise a lot of deep learning stuff, but internally, all we are doing is feature engineering and boosting, because that's what seems to get us the money. Maybe things are different now, but this is an important tool that you should be aware of. Alright. Unfortunately, I don't have time to go to other ensembles, so I will pick that up for this.